Welcome to the fifth and final lecture video accompanying lecture 24. In this video, we're going to discuss the topic of Heisenberg's uncertainty principle, and we're going to start by taking a look at the formula. And as I said in many other videos, if you want to see more of the background, the historical context, and explanation of the concepts, please look at lecture 23 and the two accompanying videos for that lecture. But for this portion, we're just going to jump right into the equation and show how to use it. Okay, so Heisenberg's uncertainty principle, as represented by two formulas, is down here on the final line of our key equations. So let's label what we're looking at and talk briefly about how we use it and then use it. Okay, so delta x is the uncertainty in position of a particle. Okay. Uncertainty in position of a particle. All right, so when I say particle, what do I mean? A wave, right? But I mean particle too. The point being that we now know that particles display wave-like behavior. We just have to be able to measure it, have a sensitive enough device or physical situation in order to measure it. So maybe that's part of the story about uncertainty, because if something is a wave, its position isn't exactly defined, right? Where would you say an ocean wave is, right? Is it at the crest? Is it at the trough? So there is an inherent principle built into thinking about particles as waves. It turns out that that idea is manifest in a little bit more complex way that we know of in modern physics, and that's the idea of a probability distribution, and Schrodinger's equation represents that in kind of the accepted modern way with some further refinement. Okay, but it does still benefits us to think of, okay, well, we have this wave, of course it's a little blurry. Okay, the other big way to think about it, the idea of uncertainty, and I don't mean to get into too much of the concepts, but the other big way to think about uncertainty is to think of it as the fact that when you measure a position of a particle, or you measure something about a particle, you are actually affecting the particle itself. It is impossible to not send a signal that affects the system in order to get the information about the system back to you as the observer. Okay, because of course, what does that signal involve? That signal involves energy, right? So it takes energy to get an energy reading. It takes energy to get a velocity reading. That energy affects the very reading that you're making. Okay, so delta P is just the uncertainty in the momentum of a particle. Momentum. Okay, so the product of those two uncertainties will always be greater than or equal to Planck's constant over 4 pi. Okay, so if one uncertainty is very small, it means the other must grow, because together they have to have a product that always has a minimum value. Okay. Now, again, not showing you a formal derivation of these, just explaining their justification. Of course, as I said before, we're going to put them in use in just a moment. The other version of Heisenberg's uncertainty, derived from the very same place, is that a uncertainty measurement in time multiplied by an uncertainty in energy must also be greater than or equal to Planck's constant over 4 pi. Okay? So here, this would be an uncertainty in a time-dependent phenomenon of the particle. So uncertainty in time-dependent phenomenon of the particle. The example I have of that is the decay of the particle, and I'll talk more about that when we get there. And then this is uncertainty in the total energy of the particle. Okay? All right. So let's take a look at the examples that relate to Heisenberg uncertainty, and those are going to show up on the second to last and the last page. Okay? So example 13 is from the previous topic, from the de Broglie wavelength, and that one's left for your practice. But let's go ahead and take a look at example 14, where we're looking at an electron. Assume that an electron is moving along an x-axis and that you measure its speed to be 2.05 times 10 to the 6 meters per second, just under 1% the speed of light, which can be known with a precision of 0.5%. What is the minimum certainty, as allowed by the uncertainty principle in quantum theory, with which you can simultaneously measure the position of the electron along the x-axis? Okay? So this is kind of a practical reality of it. It means that you really can't make a claim of any greater measurement. You shouldn't ever expect, it's physically impossible, to know the exact position of our electron. Okay? But what does that mean? How exact is it? Well, it's good to actually get a scale here. Let's do it. Okay? So we're going to go ahead and solve for the momentum of the electron, because we'll need that. So P of the electron is just going to be mv. So we'll have our mass of the electron times the velocity that we were given. Okay? And that's going to give us a value of 1.87 times 10 to the negative 24 Newton seconds. Side note, that's definitely small enough to display wave-like behaviors, because that's the scale of Newton seconds that we need. Okay? But of course, electrons display wave-like behaviors, especially when they're traveling this fast, right? If the electron is too slow, it actually wouldn't be a very good candidate for a problem like this, or for the de Broglie wavelength problem. Okay? All right. So then we're going to take 5% of that. So now our uncertainty in momentum of the electron is just going to be 0.05, so that's 5% of the momentum that we found. So that's just going to be 0.05 times 1.87 times 10 to the negative 24 Newton seconds. And that gives us 9.34 times 10 to the negative 27. It's a couple more orders of magnitude. Newton seconds. 3 more to be exact, but we're nearly on the order of negative 26. Okay? Because it's 9, right? So then we're simply going to find our uncertainty in position. I'll put the same subscript since I already put on the momentum. Okay? And we know that uncertainty must have a minimum value of h over, if you'll excuse me, it was over 4 pi. Let me double check that, because I'm looking at a different version. Sorry for flipping around. Yes, it is h over 4 pi. Because a lot of physics books use h bar. We're not using that here. So, but don't worry about if you don't know what that means. It just means I had to make a conversion. So h over 4 pi. Okay, and then of course that will be divided by our uncertainty and momentum. So delta P E. Okay. Oh. Okay, so now let's plug in our values. Okay. So 6.626 times 10 to the negative 34 over 4 pi. Okay. Divided by 9.34 times 10 to the negative 27 Newton seconds. Okay. And that's going to come out to, so this is less than, right? So that means that greater than or equal to. So it means our uncertainty in position must be greater than or equal to 5.65 times 10 to the negative 9 meters. Okay. Well, that's interesting, right? Because that's actually larger. That's 10 times larger than the atomic radius, and 10 times larger than the atomic spacing. 10 times larger, more than 10 times larger than the atomic spacing that we found for electron interference bouncing off an atomic surface. So, what does that mean, right? Well, it means that there's fundamentally fuzziness on the scale of atoms. Okay? Atoms definitely are not well-defined orbiting structures. Okay, so when we talk about the Bohr model in the very next lecture that I'll be recording for you all, in that lecture, when we talk about the Bohr model, thinking about it as a little mini solar system, we know right away that that model is wrong. Okay, because we're going back in time too, right? The Bohr model came before Heisenberg uncertainty principles were really formalized and became accepted. Okay, so there's a fuzziness at a scale that's larger than the atomic radius. All right. Okay, assuming the velocities are this high, but they will be. Okay, we are talking about velocities on that order. So I want to show you for an atom, that is. Let's look at one more, and that's the one where we're looking at time here. There we go. Okay, perfect. Mesons. Remember mesons from a relativity section? Okay, so a particular meson was measured to have an average mass of 31 mega electron volts over c squared, and an intrinsic mass uncertainty of 63 kilo electron volts over c squared. Here we use energy units of mass based on E equals mc squared, right? Because you see I'm just dividing both sides by c squared, that's it. I'm just solving for m by dividing E over c squared, right? Because this is an energy we could easily convert to joules. We could easily convert to joules, and we're dividing by the speed of light squared. Just simply using the well-known E equals mc squared. Okay? I know it's a weird way to think about mass, but it's quite useful when we're talking about small particles. Using the uncertainty principle, if the particle has a short lifetime before it decays into another particle, what will be this lifetime? Okay? And then here I'm saying that the lifetime is delta t. So we're making an assumption here. We're assuming that the decay lifetime is as short as possible. Now, I'm not a particle physicist, and I don't know if they're, what the background of that assumption is. Perhaps it's just that these particles are fundamentally unstable, so they'll decay as fast as they physically can. Well, it turns out there's a lower limit to how fast they can physically decay, because you can't decay if the very process is not well defined, right? So probabilistically, that decay can only happen once it's energetically possible for it to happen, okay? So that's the idea here, okay? We're setting lifetime tau equal to, and that's so that's its lifetime, okay, not its half-life, just its lifetime, equal to the uncertainty in time. Okay, in fact, this is actually a common approach in these introductory physics books as they introduce Heisenberg's uncertainty. I believe I put one in your study guide. So it's not always spelled out as much as I'm spelling it out now. So do take note that there is an underlying assumption here that the lifetime and the uncertainty in time are one and the same. Okay. Okay. So tau equals the uncertainty in t. Okay, and delta doesn't always mean uncertainty in every context, right? So you have to remember that we're talking about Heisenberg uncertainty. Delta t means uncertainty in t. Okay, and so then we're simply going to solve for, we're going to use the uncertainty principle, which I'll write it here. So I'm going to have tau times delta E is going to be greater than or equal to h over 4 pi. See what I did there? All I did is, the original formula is delta t times delta E is greater than or equal to h over 4 pi. I just replaced the delta t of tau, because, of course, that's what we were talking about. Okay, so then let's find what t is numerically. What tau is, the lifetime. So it'll be h over 4 pi divided by 2 over delta E. Okay, and that's going to be, and so I'm saying that it's equal to that, right? Now we know that it's an inequality, but this is also what we're setting as a value. This is the value of the value of the lifetime of the particle before it decays. Okay, that's why it's equal to, because it's equal to the uncertainty. Okay, 1.055 times 10 to the negative 34. Okay, why did I write that? Well, I actually did the math in one step. So Planck's constant, 6.626 times 10 to the negative 34 divided by 4 pi gives you that. Okay? All right. No, that's divided by 2 pi. Excuse me. That's divided by 2 pi. So we still have a 2 left over. Oh, I see what I did. I did a mistake. This should be 2 pi. In fact, that should just be 4 pi. So here, I'm just going to clean this up. I was combining things in a way that just simply didn't work. All right, because that's the thing. Okay, so there it is. H bar over delta E. Okay, of course, that's the uncertainty principle. Okay, and I won't bother combining any steps or anything because it didn't work. So 6.626 times 10 to the negative 34 joule seconds divided by 4 pi. And then that's going to be over, well, our mass. But we better convert our mass, right? Well, what does that look like? So that's just going to be R. So here I'll point out that I'm going to be using delta E as just delta M times C squared. Of course, right? Because E is delta M times C squared. Okay? So then I'll take the value that I was given. So I'll have my 63 times 10 to the third, right? Because that's the electron volt, times the conversion to joules, so 1.602 times 10 to the negative 19 joules per electron volt, and then multiplied by the speed of light. Okay, so let's see. Oh wait, here. Yeah, so I got to be dividing by c squared. I'm just checking that. Yeah, because I have to, or be multiplying by c squared, excuse me. Yep, otherwise it will not give me the units of joules that I need. Yep. No, never mind. Okay. So maybe some of you watching saw. So I was second guessing myself, but of course the units work out here, so there's no reason to. And it's just because I'm a little rusty working with these units myself, because here I'm giving you the mass, but I want the energy. Well, the energy is pretty simple. I literally just cancel out the c squared because that will get me back to the energy. Yep, of course. Okay. So this is the rest mass of the particle. Okay. Yeah, exactly. So would it matter if the particle was in motion? Yes, because it would have a different total energy. We'd have to take the rest mass plus the kinetic energy. But here we have a meson at rest, and that matters, right? That actually changes the lifetime. Cool. Okay. So we're good there with our rest energy. So we can go straight from that to the final step of just calculating it. Okay. And we're good. We're going to get units of time because the joules are going to cancel. Yep, and we'll just be left with seconds in the numerator. Perfect. Okay. Figured I would check my units after that confusion. 5.23 times 10 to the negative 21 seconds. There we have it. Okay, so if this meson is fundamentally unstable, the shortest lifetime it can possibly have is 5.23 times 10 to the negative 21. Okay? Okay. Could it have a different lifetime? Could it have a shorter lifetime? Sure, if we know less about its mass, right? But if we know its mass to be that small, right, then we know its lifetime is that. Okay, so different approach, right? Because the previous example was all about kind of uncertainty in the experimental sense. Here it seems to be uncertainty kind of playing the role of fundamental characteristics of the particle. So kind of be aware of the two kind of versions of Heisenberg uncertainty problems, and just make sure to be able to follow the units and follow the steps and make the most sense of it. All right. Well, thank you very much for watching. Oh, but before I go, I'll point out that I'm leaving a couple examples. 15 should be quite kind of similar for the practice. 17 is kind of fun. Didn't need a whole page, but it got pushed onto the last page. In this case, you're just finding the uncertainty in something that's macroscopic, right? So if I know that a baseball has a velocity of 42 plus or minus 1.5 meters per second, well, the uncertainty is the 1.5 meters per second. And so that's going to be what I'm going to use to find the uncertainty in the position of the baseball, right? Does that mean the baseball might not be where I really think it is? Well, sure, but the deviation from where I think it is going to be so small that it would never be practically measured. Okay, that's the thing about, so macroscopic objects are really where they appear to be. Okay, you're not just going to like suddenly end up on the other side of the wall because you as a particle had a probabilistic chance of that happening. It's infinitesimally small, the chance of that is. Okay. Furthermore, I do want to point out here one last thing about example 16 is I didn't use the actual average mass. I just used the uncertainty in the mass. And I think I kind of maybe didn't portray that as clearly at the very end when I was speaking. But so I was actually using the uncertainty in the mass in order to find the minimum lifetime. Okay. So now, thank you very much for watching.